Okay, so let's pick up part 2 in our additive manufacturing design process lecture, and we'll pick up. We just finished discussing what the STL file for the cube looks like. So now let's have a little bit more of a look at how curves are represented in STL models. So remember, STL files can only approximate curves, so we can't actually create a true curve shape. Curves are approximated with triangular sections, so you get this faceting. That's the term, faceting look to our curves. And the number of triangles that you use to represent those curves, obviously the more triangles means you're going to have smaller facets, which means the shape is going to appear more curved, but you're sacrificing file size. So in this case, if we took a 10 centimeter sphere, right, CAD model 10 centimeter sphere, and with 1 millimeter precision, it would be, we could approximate that with 506 triangles, right? That would have a file size of approximately 0.13 megabytes, all right? If we then increase that to, same 10 centimeter sphere, but now 10 micrometer precision, the triangles are going to zoom up a factor of 100 to 50,000 triangles. And your file size is then going to go to 13 megabytes. So from 0.13 to 13, another factor of 100. But if possible, we still want to increase the triangles in highly curved regions. Okay. The issue is file size nowadays. It used to be an issue with computers, right? Nowadays, computers really, and hard drive space and file transfer really doesn't have an issue with large file sizes. If you do have a computer with issues with large file size, then of course, then you might have to chunk it down and reduce the number of triangles. But for the most part, this is not really a big issue. The shape right here. So what we've done in this example here, and there is some software that can do this. Notice that with large curves, right, or certainly planar regions, we do not have to have a large number of triangles. But as the curves get smaller and tighter in this region here and in this region down here, we want to increase the number of triangles to better approximate that curve. So there is software that can do that can selectively assign more triangles or less triangles to different areas. You would need special STL file software like Mesh Mixer or some other more advanced STL file repairing and editing software. But it is possible, and this is what we're talking about with controlling where the STL file applies more or less triangles to a shape. Okay. So there are problems with STL files, as you probably have figured out from our discussion with curves and such. So an STL file is created by applying a mesh to a surface of the object. Okay. That mesh has triangles on each mesh face. All right. And the common errors that we see with that, and keep in mind, these errors for the most part are confined to 3D scan data. We really don't have these errors in CAD model files. So, solid models, are not going to have these same errors, but surface models and scan data are going to have, errors like this. So we have a vertex to vertex rule, which means that, this kind of shape right here, because we have a node or a point on these two triangles that is in the middle of this triangle, this is not going to be a valid, planar region, right? This would need to be composed of 4 triangles, and we see right there. So we need a vertex to vertex rule. Okay. That is to say, we can't have a vertex just kind of hanging out here in the middle of an edge. We also want a watertight mesh. That is, we don't want any holes in it. All right, any missing surfaces. And we want all outward facing normals. So this is an example of a cube with all outward facing normals. The black arrows are our normals. If one of these triangles has the vertexes defined in the reverse direction or the wrong direction, the normal is going to be pointing inside, and that's going to create an error. That's going to cause an error on this STL file, and it won't be able to be 3D printed. Unnecessary surfaces are also something that you don't want to have in there. A lot of times, bad data will have a triangle over another triangle, right? Or a triangle just floating out there in space. So we want to clean those up before we send them to the 3D printer. Now, there is an alternative to the STL file, and this is gaining a lot of fans, a lot of applications, and in many cases, 3D printers nowadays will use this file format. It's called the Additive Manufacturing File Format, the AMF file format. It's become very popular. It's very useful, especially if you have color printing capabilities, because as we see, one of the benefits of this is that it can print in color. Or it can contain color data that the STL file normally strips out. So the AMF is an open standard improvement on the STL file format. The ISO ASTM standard 52915 talks about or discusses this AMF file format. The STL file format, the advantages of this are it's the de facto standard, right? Because it was the first one, it's the standard. I don't know whether that's a valid use of a standard just because it's the first, but it's also very simple to read, write, and process. Very, very simple. The disadvantages is that it can have duplicate information, leaks and inconsistencies can exist. It does not scale well to high resolution or lattices, okay? And it does not support color, material, or orientation. All right. All of these things are fixed with the AMF file format. So the additive manufacturing file format was developed to address any machine to build the part to the best of their capabilities. It's simple, allows implementation and easy understanding. It's scalable, right? So we can scale up an STL file quite easily using the AMF format. The performance is better than the STL file, even though the STL file still performs pretty well. It's backward compatibility, so we can go from an AMF format to an STL file. And it has future compatibility, so it has the allowance to incorporate new features introduced in parts on machines that we don't actually have in existence right now. So the AMF introduces new features beyond the STL format. So it has curved triangles, right? Improves geometric accuracy of curves, right? So basically each node, now notice each node has a normal rather than a surface normal here, which really wouldn't be defined with a curved vertices, right? That's going to make curves look better. It has color properties, so we can maintain the colors that are assigned to the different regions. This is important if you're using a 3D printing process that allows color. So many of the material jetting printing processes have color. Some of the SLS processes have color. Even some of the material extrusion processes can use color from different filaments. So that's important to incorporate in that. We can do texture mapping. Image texturing can be applied. And volumes can be assigned to different material. And microstructure, lattices, internal lattices, regions can be applied. Now, this is important because especially in like vat photopolymerization and powder bed fusion, the lattice structures are very common, very advantageous to use the lattice structure to maintain that strength to weight ratio, or to actually improve the strength to weight ratio. This microstructure is not easily done with the STL format, but in the AMF format, it can be done. And part constellations, duplicate objects can be packed and arranged more efficiently. So there's a lot of benefits to doing this. If your 3D printer can use an AMF file format and you can create an AMF file, I encourage you to use this to play around with it. All right, so let's move on to stage 3 then. STL file manipulation and editing. So we've already talked about STL file can have errors in it. So many additive manufacturing machines and software will automatically fix some of these issues. I know that I use GrabCAD. Oftentimes will fix these errors. It will notify you, hey, I found an error, and then it will say, click here to fix it. So some of these errors are very easy to fix. It's especially critical for scan data. That's, as I said, that's where we see a lot of errors. External STL editing software can also be used, such as NetFab, Magix, or Mesh Mixer. Possible editing actions include increasing or decreasing the resolution, i.e. the number of triangles in the specific areas, repairing the STL file itself, scaling the model, reorienting the model, or repositioning the model, reorienting the model, segmenting the model, that means breaking it up into 2 or more segments, adding features. These are not repairs, but these are things that we can add. We can add an embossed or an engraved feature with some of the more advanced STL editing software. So this would be features that are not in the CAD data themselves. Same with segmenting. So if you need to break it up because, let's say, your print bed is only a certain size, your CAD model is too large, some of this software some of the STL editing software will allow you to break your part up into segments so that it can be put back together again. And it can create or edit different support structures. A lot of 3D printers and additive manufacturing experts will like to assign their own support structures based on their experience with printing. So then moving on to stage 4, build file creation. This is where we send our STL file or AMF file into the slicing software. All right. So the AM machine software, right? That is the software associated or part of the 3D printer, performs 2 actions requiring user input prior to printing. So first, it slices the file. All right. So the layer thickness is a setting that you need to adjust on your 3D printer. Layer thickness will impact part accuracy and is limited by machine capabilities, right? The layer thickness is going to be set to a minimum or maximum value. From our 3D model, we can see that when we have thicker layers, we're going to have a more stair-stepped approximation of our surface, right? With thinner slices, we're going to have a better approximation of the curves for our surface, but obviously the printing is going to take longer and the file is going to be larger. Adaptive slicing is special slicing software where we can, and not all printers can do this, right? Not all slicing software does this, where we can adjust the thickness of the slices depending on whether we're printing more or less vertical sections or curved sections. Okay, so this is, like I said, the staircase error. And we also want to set the interior fill pattern, or what we call infill, right? So this is the infill pattern. How it's represented is in our 3D print is going to be determined in the slicer software, whether we want some kind of hollow core, whether we want it solid. These are not done in our CAD software or in our scan data, right? Remember, the STL file is a hollow surface representation. It has no interior volume or mass. And so the interior fill is determined in this stage, the stage 4, with the build file creation. There's a lot of variety for infill. A lot of the 3D printers now give you quite an array of patterns for our infill. Most of them are designed to maintain strength, but reduce the weight. Or even reduce the material usage. Sometimes they just have really neat patterns on them. All right, so that brings us to step 5, machine setup. All right, different AM processes have different machine requirements for the setup. Not only different processes, but different machines have different requirements for their machine setup. So it's incumbent upon the person that's going to be doing the printing to know and be able to set up their machine properly. Common procedures include setting the software parameters, preheating the build chamber, sifting the powder if you're using a powder process, making sure your resin levels are sufficient and topped up, loading the filament, and filling any of the gas-filled chambers that you would need. For most AM systems, this step is fully automated. This is step 6, stage 6, model building. Okay. So once we're done with stage 5 and we've set up our machine, then we're ready to hit that button and start the printing process. And most of the times, this is a fully automated process where the printing occurs. It can take anywhere from minutes to hours, depending on your process, the printer, and what you're printing. But when you're done, you're going to have a finished part and you're ready to move on to stage 7. This can be either post-processing, including part removal and cleanup. So here we're going to remove the part from the build plate, or remove the powder that's left on the part that's not solidified or sintered or whatever. Removing the support material around the part. Dipping the part into the solution so that the support material can be dissolved. Or photo curing in the case of resin processes. All right. So this is the part removal and cleanup part of stage 7. Remember that we also have the finishing part of stage 7. So I guess we could say stage 7 part B is finishing. Not all designers choose to finish their part, but in many cases it is necessary, especially for the metal parts. So this is going to improve the durability, strength, and or appearance of your part. This could include sanding, painting, tumbling the part, infiltrating it, machining, shot peening, bead blasting, electroplating, heat treating it, curing it, or sealing and smoothing it. Okay, so a lot of options here. Looking at some of the common post-processing methods, right? Stage 7, common post-processing methods with some common 3D printing processes. So here we have selective laser sintering, which is powder bed fusion, but with plastic powder. SLA is our resin stereolithography, vat photopolymerization. FDM is material extrusion with plastic. This is probably the most common 3D printing process out there, especially when you take into account home 3D printers or school 3D printers. And then laminated object manufacturing, which is our sheet based. So what are the post-processing tasks that are common for these? So cleaning is required in all of these, right? You got to clean the part when you're done, right? Post-curing, SLS typically doesn't involve post-curing. SLA does, right? Post-curing, in a, or photo curing in a light, area. And as you can see down here, all of these processes are capable of undergoing a finishing phase or finishing step, depending on what you want to do. Okay. That doesn't mean that you have to finish it. It just means that you can. All right. This is some, I found these on the internet just to kind of show you the variety and the quality. All of these prints are finished, right? And you can see up here, these are all, by the way, these are all FDM or plastic models. So these are all created. I believe they're all created using the material extrusion process, the one that you are probably most familiar with. But you can see up here, this is using a vaporing process, right? So we can smooth out, and look at that. That's a very nice finish on this. I guess that's a bunny rabbit or something like that. This Stormtrooper helmet has a fantastic color on it. Some of these are painted, right? So you can finish it so that you can then paint it. Again, this looks fantastic. And this is really neat because we have a textured appearance here with a high gloss finish here. So there's a lot of cool things we can do with finishing. There's a lot of variety. Obviously we're not going to go into much depth here with finishing operations because it's very particular to the actual process, the actual machine, the actual material you're using. But there's a lot of variety here. And if you're interested in that, I encourage you to dive deeply into those processes. All right, so that concludes part 2 of the additive manufacturing design process. So in the next lecture, we'll start to look at the 7 standard processes for additive manufacturing. And the first process that we're going to look at is vat photopolymerization. So I'll see you then.